Okay. Good afternoon, one and all. Myself, Supriya Nayaka, host of this program. Welcome to 126th Creative Online Weekend Talks, gateway to a world of learning and exploration. As we gathered here under the tagline of Knowledge Square, sharing of knowledge increases our knowledge or doubles our knowledge. It is privilege to extend a warm welcome to each of you. Creative organize online weekend talks on every Saturday and live stream on our YouTube channel Creative GBD. Creative vision is to build a constructive thinking on various domains rather than non-textual, non-syllabus related concepts. Today is a special day in the realm of our sharing curiosity as Creative proudly introduce a luminary in the field of space exploration, recognized as Space Tutor by ISRO. Our guest speaker will unravel the mysteries surrounding and implementing space adoris that 126th talk brings to you an deepen overview of XPOSAT, a space mission set to grace the skies on January 1st, 2024 from the iconic launch site at Sriharikota. Today, we have Krishnamurti, yes, sir, with us today, and an electronic and communication engineer from UVCE, Bangalore. Join us as our esteemed resource person with a career at the Raman Research Institute since 1995. Krishnamurti sir specialized in radio and X-ray astronomy, instrumentation, hardware and software, currently contributing to the X-ray team. He is actively involved in developing the Felix payload from the upcoming XPOSAT space mission. So we are welcoming you, sir, for this creative session. And I welcome one and all for joining with us. Over to you, sir.
Thank you, madam. And thank you, Ms. Supriya, and the proactive, creative, proactive, creative team for giving us an opportunity to present this titled talk. I'll share the screen. Just 1 minute. Yeah, is the screen visible?
Yes, sir.
Yeah. Yes. Audio is clear, right?
Yes, sir.
Yeah. So once again, thank you, Ms. Supriya and the proactive creative team for giving us this opportunity to present the titled presentation and overview of the XPOSAT space mission. Actually, I'm basically working for the Polix team. In the due further slides, I'll explain about the rest of the things. So on behalf of the Raman Research Institute, I wholeheartedly appreciate the creative team for this intuitive initiative. Actually, this is a very happy and special moment for me to share that Raman Research Institute has successfully celebrated 75 years of scientific excellence, and XPOSAT project is also just completed, and it's ready for launch. So in this presentation, I would like to mention a few basic aspects of X-rays related to this payload, and then move on to the payload development. I'm sure many of you may be better aware of me about the subject, but I thought for the benefit of a few others, I thought of including a few slides that covers on basics. So ಅದಕ್ಕೆ ಕ್ಷಮೆ ಇರಲಿ. This is Indian X-ray polarimeter. We named it as POLIX, POLIX, onboard X-ray polarimeter satellite XPOSAT. So I'm privileged to say a few words about Professor Bishwajit Paul here. Professor Bishwajit Paul is an eminent scientist and an astronomer at Raman Research Institute in Astronomy and Astrophysics Group. He primarily studies rotating neutron stars and black holes in the galaxy and its satellites. His favorite is X-ray stars. Professor Bishwajit Paul is PI for the POLIX instrument that is one of the payload in XPOSAT. Yeah. So coming to this EM spectrum slide, all of us are very familiar with this EM spectrum picture that is shown here. For today's discussion, we will concentrate on the X-ray region that is here at this point. This X-ray, the EM spectrum shows all radio, micro, infrared, visible, and all that. But our interest for this thing is X-ray. So all of us, why do we need this satellite for this high energy X-ray observation? One thing about these X-rays compared to other bands in astronomy activities is that what happens is the celestial objects emit X-rays, but we will not be able to observe them from the ground. The reason is that the atmosphere is relatively opaque to this. So to observe X-ray activities, we need to put a telescope well above the atmosphere. And the present option is to use only satellites or spacecraft platforms to gather data for such studies. So these pictures shows the atmosphere absorption percentage to different wavelengths, and X-rays lie in this region. I am here down. This is the absorption, atmospheric absorption from 0% to 100%, and the X-rays are in 1 nanometer wavelength. So we are Earth atmosphere is it's completely opaque for this. So we will not be able to reach get the signals from sky. This is a telescope on Earth that we can use it for the radio. Then here in this picture, up to here, one can go with balloons. So here is the X-ray region where we need satellites. So, okay, why do we need this X-ray astronomy? See, other than visible light, cosmic objects do emit electromagnetic radiation over a very wide range of wavelength or energy. So as I showed you in the previous slide about the EM spectrum, like highest density, some extreme physical conditions of the universe, like the highest density, strongest magnetic field, strong gravity, highest temperatures, etc., are found around the special kind of, very compact stars like neutron stars and black holes. ಆಕ್ಚುಲಿ ಏನಾಗುತ್ತೆ ಅಂದ್ರೆ ಈ ಭೌತಿಕ ಸ್ಥಿತಿಗಳು ಏನಿರುತ್ತೆ ಅದು ಹೆಚ್ಚಿನ ಸಾಂದ್ರತೆ ಇರಬಹುದು, ಅಥವಾ ಬಲಿಷ್ಠವಾಗಿರುವಂತ ಗ್ರಾವಿಟೇಷನಲ್ ಕಾಂತಕ್ಷೇತ್ರ ಇರಬಹುದು, ಅಥವಾ ಗುರುತ್ವಾಕರ್ಷಣೆ, ಅಥವಾ ಹೆಚ್ಚಿನ ತಾಪಮಾನ, ಅತ್ಯಧಿಕ ಉಷ್ಣತೆ, ಹೀಗೆ ವಿಶೇಷ ರೀತಿ ನಕ್ಷತ್ರಗಳ ಮೇಲೆ ಕೂಡ ಇದು ಕಂಡು ಬರುತ್ತೆ. ಈ ನಕ್ಷತ್ರಗಳ ಉದಾಹರಣೆ ಅಂದ್ರೆ ಲೈಕ್ ನ್ಯೂಟ್ರಾನ್ ಸ್ಟಾರ್ಸ್ ಇರಬಹುದು, ಅಥವಾ ಬ್ಲ್ಯಾಕ್ ಹೋಲ್ಸ್, ಕಪ್ಪು ಕುಳಿಗಳು ಅಂತ ಕರಿತೀವಿ ಕನ್ನಡದಲ್ಲಿ, ಬೃಹತ್ ನಕ್ಷತ್ರಗಳು, ಮತ್ತೆ ಇದೇನಾಗುತ್ತೆ, ತಮ್ಮ ಸಾಮಾನ್ಯ ಜೀವಿತ ಅವಧಿಯನ್ನ ಕೊನೆಗೊಳಿಸಿದಾಗ ಮತ್ತೆ ಇದು ಸೂಪರ್ನೋವಾ ಸ್ಫೋಟ ಆಗುತ್ತೆ. ಎಕ್ಸ್ಪ್ಲೋಷನ್ ಆದಾಗ ಆ ಸ್ಟಾರ್ದ ನಕ್ಷತ್ರದ ಮಧ್ಯಭಾಗ ಕುಸಿದು ಇದು ಒಂದು ತಟಸ್ಥ ನಕ್ಷತ್ರ ಅಥವಾ ಒಂದು ಬ್ಲ್ಯಾಕ್ ಹೋಲ್ಸ್ ನ ಕ್ರಿಯೇಟ್ ಮಾಡುತ್ತೆ. ಈ ಕೆಲವೊಮ್ಮೆ ಏನಾಗುತ್ತೆ, ಈ ಬಲವಾಗಿರುವಂತಹ ಈ ಕಾಂತೀಯ ಕ್ಷೇತ್ರಗಳೇನಿದೆ ಇದರ ಪರಿಸ್ಥಿತಿಲಿ ಕಾಂಪ್ಯಾಕ್ಟ್ ನಕ್ಷತ್ರಗಳು ಅವುಗಳಿಂದ ಉತ್ಪತ್ತಿ ಆಗುವಂತಹ ಎಕ್ಸ್ರೇಸ್ ಅಂದ್ರೆ ಕ್ಷಕಿರಣಗಳು ಅಂತ ಕರಿತೀವಿ, ಎಕ್ಸ್ರೇಸ್ ನ ಬಳಸ್ಕೊಂಡು ನಾವು ಬಹಳ ಒಳ್ಳೆ ಅಧ್ಯಯನ ಕೂಡ ಮಾಡಬಹುದಾಗಿದೆ. ಸೊ ಈ ಭೂಮಿ ಮೇಲೆ ವಾಯುಮಂಡಲ ಈ ಎಕ್ಸ್ರೇಸ್ ನ ನಾನು ಹಿಂದೆ ಹೇಳ್ದಂಗೆ ಅದು ಹೀರ್ಕೊಳ್ಳೋದ್ರಿಂದ ಉಪಗ್ರಹಗಳನ್ನ ಬಳಸ್ಕೊಂಡು ಮಾತ್ರ ನಾವು ಬಾಹ್ಯಾಕಾಶದಿಂದ ಈ ಅವಲೋಕನ ಮಾಡೋದು ಅವಶ್ಯಕ ಆಗುತ್ತೆ, ಮತ್ತೆ ಇದು ಅನಿವಾರ್ಯ ಕೂಡ ಆಗುತ್ತೆ. ಸೊ ಈ ನಕ್ಷತ್ರಗಳಿಂದ ಹೊರಹೊಮ್ಮುವಂತಹ ಎಕ್ಸ್ರೇಸ್ ಗಳ ಧ್ರುವೀಕರಣ, ಅದರ ಗುಣಲಕ್ಷಣಗಳು, ಮಾಪನಗಳು ಇವೆಲ್ಲ ನಮ್ಗೆ ಇದರಿಂದ ಕಂಡು ಬರುತ್ತೆ. ಇದರಲ್ಲಿ ಸಿಂಕ್ರೋಟ್ರಾನ್ ವಿಕಿರಣ ಅಥವಾ ಈ ಎಕ್ಸ್ರೇ ವಿಕಿರಣ, ನ್ಯೂಟ್ರಾನ್ ಸ್ಟಾರ್ ಮುಖಾಂತರ ಬರುವಂತ ತೀವ್ರವಾಗಿರುವಂತಹ ಒಂದು ಕಾಂತೀಯ ಕ್ಷೇತ್ರ ಇದ್ರ ಮೂಲಕ ಹಾದು ಹೋದಾಗ, ಅಥವಾ ಬ್ಲ್ಯಾಕ್ ಹೋಲ್ಸ್ ಅಂತಹ ಒಂದು ಬಲವಾದ ಗ್ರಾವಿಟೇಷನ್ ಇರುವಂತ ಕ್ಷೇತ್ರದ ಉಪಸ್ಥಿತಿನಲ್ಲಿ ಈ ಎಕ್ಸ್ರೇಸ್ ಚದರಿ ಹೋದಾಗ ಈ ಲಕ್ಷಣಗಳನ್ನ ನಾವು ಇದರಿಂದ ಮಾಡಬಹುದು. ಲೈಕ್ ವಾಟ್ ಐ ಮೀನ್ ಟು ಸೇ ಇಸ್ these massive stars end their normal life and have supernova explosions. The core of the star collapses and forms a neutron star or a black hole. These compact stars are best studied using the X-rays produced by them, sometimes in the presence of strong magnetic fields. As the Earth atmosphere absorbs the cosmic rays, it is necessary to make these observations from space using satellite, as I said earlier. So the measurement of the polarization properties of these X-rays from these stars can tell us about many important aspects. When X-ray radiation is produced by electrons moving through magnetic field, that's also called synchrotron radiation, or when X-ray radiation passes through the intense magnetic field of a neutron star, or when X-rays are scattered in the presence of a strong gravitational field of black holes, the emergent X-rays are polarized. I mean, that is what we mean polarization studies. So I'll just quickly play this 1 minute video which will tell us about what I was trying to explain.
But a far more interesting case involves close.
Is the audio available? I mean, you are able to hear?
Yes, sir.
Okay, fine.
Binary systems. This is when the stars are very close together, orbiting around their center of mass quite rapidly. Sometimes they are so close that the gravitational distortion produced causes their stellar atmospheres to exchange material, or they could even be so close that they are in direct contact with one another, such as this system with two large, hot, main sequence stars practically overlapping. This is most fascinating when one star is a compact object, like a white dwarf star, neutron star, or black hole, as this object will begin to pull matter away from the other object in the system until a dramatic event occurs. If a white dwarf is causing the accretion of gas from another star, it becomes a cataclysmic variable star, where the incoming gas gets very hot and emits radiation. We sometimes call such an object a vampiric star, as it is almost as though it is sucking the essence out of its companion star like a vampire. If instead the compact object is a neutron star or black hole, this is called an X-ray binary, which can be either a low mass or high mass X-ray binary, depending on the mass of the donor star, which is the other star in the system feeding the compact object with material. One fascinating binary system is called AR Scorpii. This is a binary pulsar, which consists of a white dwarf pulsar about the size of Earth and a red dwarf star. Pulsars are highly magnetized objects that emit powerful beams of radiation in a rapid periodic manner. Typically, pulsars are neutron stars, but sometimes they can be white dwarfs as well, though being much less compact than neutron stars, they rotate more slowly. AR Scorpii contains the first object of this type that was ever discovered. We should note that binary systems can have complicated evolutions. Take, for example, a binary system with two fairly large main sequence stars, which form with around 15 and 20 solar masses respectively. We know that stars of this size evolve rapidly, since the inward gravitational pressure is so strong that fusion occurs at a furious pace, burning through the hydrogen in the core much faster than in smaller stars. Eventually, one star enters a phase of expansion and will exceed its Roche lobe, meaning that it juts far enough into the gravitational field of the other star that one will begin to pull material away from the other. This material may form an accretion disk, as we saw previously, but it can also be absorbed through direct impact, as shown here. We see the blue star acting as the vampiric star, rotating faster and flattening out. We also see that an enormous percentage of the other star's mass is being transferred in the process, actually the majority of its mass. This star is now so much more massive that fusion increases even more dramatically, which generates a stellar wind that causes the other star to become very small. Eventually, this star will go supernova and leave a tiny neutron star behind, potentially escaping the system altogether. The vampiric star will then reach a red supergiant phase where it expands immensely, after which it too will go supernova and leave a neutron star behind. So we can see that stellar evolution is much more complicated in binary systems due to the influence each star has on the other. There are so many
Okay, yeah, this is a demonstration of what I was trying to tell. I think I thought this may be giving ಒಂದು ಅರ್ಥ ಮಾಡ್ಕೊಳ್ಳಿಕ್ಕೆ ಚೆನ್ನಾಗಿರುವಂತ ಒಂದು ವಿಡಿಯೋ ಅಂತ ನಾನು ತೋರಿಸ್ತಾ ಇದ್ದೀನ. Okay, fine. So coming to this space missions, what we have, I mean there are few things. See, in any cosmic source, usually the light comes from it, and light has four different information that we can get it. So if we come to imaging, which is, see, I've just listed a few missions here, Chandra X-ray Observatory, then RXT, XPOSAT, NICER, and Hitomi. So, and why it is used, I mean, how it is used in this astronomy, X-ray astronomy thing. So, direction of the light directly coming from the source is called imaging. And secondly, it is the energy or the wavelength of the light that is called spectroscopy. Thirdly, there is the time at which the X-ray event has come, which means that the source has come out where it is generated. This is called polarimeter time. So what happens is, see, these three techniques are very well developed, and a lot of things have been done over the past 4 decades or so. But polarization is the one of the polarization, like this information, which has been explored very lately. And Polix is the second mission out of this previous missions. Yeah, so this slide shows about the XPOSAT space mission. XPOSAT is a science mission and collaboration project of ISRO and RRI. It contains 2 payloads, Polix and Expect. Everything other than Polix has been developed by ISRO. X-ray polarization measurement is, a very difficult and though there have been about 30 X-ray astronomy missions by many space agencies, including some from India. So far, there has been only one X-ray polarimeter mission by NASA in 2021. The second such mission, XPOSAT, is to be launched by ISRO. All of us are aware, and Supriya Madam also told in the beginning that this moment that it's on the first day of New Year, 1st Jan 2024. Yeah, okay. So the X-ray polarimeter instrument, POLIX, for this mission, which detects higher energy X-rays than NASA's IXP mission, has been, this is designed and developed by the prestigious institution Raman Research Institute at X-ray Lab in collaboration with ISRO. It is an entirely made in India instrument. And see, the XPOSAT contains, as I said, POLIX is used for polarization measurements, and polarimetry provides information about the structure and physical process that I explained just now. And XPECT is used for spectroscopic measurements. Spectroscopy provides, detailed information about, temperature, density, chemical compositions, and motion of the emitting material in the astronomical objects, and so on. This helps astronomers in understanding the physical conditions and processes occurring within stars, galaxies, supernova remnants, and other cosmic sources. So we have extracted Indian POLIX name, the word, from Indian X-ray polarimeter. We're calling it as POLIX. And X-ray spectroscopy and timing payload, we have extracted a few characters, and it is called XPECT. So on-board X-ray polarimeter satellite, we are calling it as XPOSAT. And IXP is will be, this is working between 2 to 8 kilo electron volt, which is, soft X-rays, and 8 to 30 kilo electron volt is where POLIX is going to work. This is where we are. Yes. Now, sources that will be investigated with POLIX. Why do we need? Why are we doing this? So, if you see the first picture here, wherein I've written as pulsars, magnetic field structure of neutron stars, and properties of matter in extremely high magnetic field. There is a neutron star on which the matter from the companion star is falling. In this figure, you can try to visualize that. So X-rays come out from the region shown in this figure. Since X-rays come out from such strong magnetic field, which is around 10 power 12 Gauss kind of value. So this will be polarized since it comes out through a strong magnetic field. And so we want to study the polarization of this magnetic field, which will help us study the magnetic field structure of this neutron stars and the properties of matter in extremely high magnetic field. And coming to this second picture, where I've written crab pulsars and nebula, X-ray emission mechanisms in rotating high magnetic field neutron star and outflow of high energy charge particles. See, there is a similar neutron star at the center where a crab pulsar is radiating. That is an isolated neutron star. It is not accreting. However, this neutron star has a very high magnetic field and is rotating very fast. This rotating magnetic field actually produces an extremely strong electric field that causes the outflow of charged particles. And surrounding nebula is also radiating. Actually, the image is made from the radiation coming out from the nebula. There is a fast rotating neutron star with a speed of 30 times a second that also has magnetic field of about 10 power 11 Gauss. In such a strong magnetic field, there is a rotation that creates outflow charge particles that energizes this whole region. That is the center thing in the pulsar. The neutron star is the pulsar, and the rest of it is the nebula. X-ray emission mechanism in rotating high magnetic field, neutron star that is at the center and outflow high energy charge particles from the neutron star, actually that comes out. So that energizes. So there will be a magnetic field here, which will help us in understanding the magnetic field structure and speeds and so on. So now we will come to black holes. Actually, the black hole itself doesn't emit any X-rays, but the material surrounding emit X-rays. So measuring polarization from those X-rays help us understand some details of the high energy emission. This X-ray emission of around 2 to 8 kilo electron volt, and SWAN is studied by NASA. While the X-ray emission of 8 to 30, as I mentioned in my previous slide, kilo electron volt will be studied by POLIX. Coming to POLIX instrument overview. This instrument is to measure polarization, where we are going to get degree and direction of polarization. Energy band, as I said it is between 8 to 30 kilo electron volt. I'll explain what is photon collection area in the next couple of slides. With this payload, we can obtain the degree, as I said. I mean, actually, for about for very bright sources, the energy range can be extended up to 50 kilo electron volt. And these are all some POLIX specifications. Let me highlight a few important parameters of this POLIX. You will get to know in the future slides. The photon collection area, energy range, field of view is 3 degree by 3 degree with plus or minus 0.2 degrees flat top response. And there are detectors used, or the position sensitive proportional counters. The total mass of is around 130 kgs, around 68 watt kind of raw power. And the data generation per day will be around 6.5 gigabits maximum. Scatterer used is beryllium. The lifetime of this is 5 years, but it can extend. The modulation factor is between 40 to 44%. Then 8% MDP for 200 milligrab sources as sensitivity with 1 megasecond exposure. Okay, these are all some specifications that I told you. Now let's come to principle of how it works. What is the principle of operation? See, the rotation around the viewing axis, where I've shown incoming photon. This is carried out during source observation to carry out polarization measurements. The incoming photon will get scattered from the beryllium scatterer that I've mentioned here as scatterer. If the incoming photon is polarized, then it has a higher chance of getting scattered in the perpendicular direction, that is perpendicular to the electric field vector shown here. And that is how polarization is measured. However, these polarization will not be the same for all incoming vectors. So we plan to detect a net polarization the rate, in the count rate. and for unpolarized sources, a uniform count rate is expected. This is in the graph that is shown below. There is azimuthal modulation from polarization. Polarized sources are here, and then this is the uniform count rate with unpolarized sources. This is angle versus count rate is the plot. So yeah, this is the detector, and as I explained, the photon gets in, and there is a perpendicular, the thing, and then it goes to the detector. I'll explain these things in the next next slide. Yeah, and with respect to my previous explanation, I mean, why do we need spinning? For POLIX to measure X-ray polarization, we require the satellite to be spinning around the viewing axis, and the viewing axis has to be aligned with the collimator axis within 0.1 degrees during rotation, and spin rate is around 0.2 revolution per minute. As I mentioned earlier, rotation around the viewing axis is carried out during source observation to carry out polarization measurements. So yeah. So what all it contains? I mean, XPOSAT contains these blocks. See, it has. Let's start from passive elements, collimator, and there is a high purity beryllium scatterer, and there are 4 xenon proportional counter detectors, and there are some backend electronic systems that are sitting here, and expect detectors are there, and the field of view of this collimator is 3 degrees by 3 degrees, and this is the inside view of back detector inside is shown here. Yeah, this is the collimator which I showed you in the previous diagram. This is a passive element that restricts the field of view of 3 degree by 3 degrees, and then there are 747 hexagonal tapered slots that are made, and the flat top response is 0.2 degrees. That compensates inaccuracy in satellite pointing. The collimator axis is aligned to the pitch axis of the satellite within 0.03 degrees. Yeah, so this is a scatterer. It's just mounted on the base plate. It's also a passive element mounted on payload base plate. Consists of this is a beryllium disc clamped on a aluminum holder. Actually, beryllium is used here to minimize the effect of photoelectric absorption of photons in the scattering element. That's a low atomic mass material. That's the reason it's preferred to be beryllium. Yeah, this is the detector system. Like we have the collimator, and there are 4 detectors connected in this fashion, which I was showing you earlier. The mechanical configuration of the detector system, we have scatterer, 4 detectors, and a cyclic symmetry to cover all sides of the scattering element. A collimator, as I said, it's to reflect the field of view. I mean, restrict the field of view. Yeah. This is one of the detector is removed just to have a clear picture how it looks like. Sorry. The detectors, and you can see some anode wires. Scatterer is sitting below. I'll explain these things next. Yeah, detectors, POLIX detectors are basically position sensitive, multi-wire proportional xenon gas filled counters. It consists of 4 main parts: detector housing, wireframe, a mylar window, and the top plate. So actually, for understanding these detectors, there are 4 different ways in which polarization of X-rays manifest in their interaction with matter. So we have Bragg reflection, photo electron emission, Thomson scattering, and Compton scattering. The instrumentation of X-ray polarization measurement is therefore vastly different based on the method used. The Bragg reflection method works in a very narrow energy band, and in the hard X-ray band of Compton scattering, there are very few X-ray photons from the sources, both giving low sensitivity for X-ray polarization measurements. Between photoelectron polarimeter and Thomson scattering X-ray polarimeter, the former requires extremely small pixel X-ray detectors and X-ray focusing optics, which is not suitable for a small satellite. We have therefore selected the method of Thomson scattering, which is the exclusive method in this band, say 10 to 30 or 8 to 30 kilo electron volt, and can be extended to 5 to 50 kilo electron volt range. As I was telling you earlier, some cosmic sources like the accreting X-ray pulsars are the brightest in this energy band, as the low energy X-rays from these sources are often absorbed by the interstellar medium, and the sources have a steeply falling spectrum at high energy. So, sorry, 1 minute. Yeah, yes, Thomson X-ray polarimeter is therefore a very suitable solution to study these sources. So this is the exploded view of the detector. There is a detector housing at the bottom, and above that there is a wireframe, and there is mylar window, and the top plate or the window support plate. It's filled with, the final assembly will be filled with xenon. Yeah. So this is the wireframe, and you see here there is a main anode of 25 microns thick nichrome wires, and anti-anodes are used. That's a 25 micron gold coated SS. Cathode is 50 microns beryllium copper. So there are 12 anodes. The big, the larger diameter bushes, what you see are the anodes. The middle, the smaller ones are anti-anode, and the pins are cathode. So there are totally 12 anodes, 30 anti-anodes, and 354 cathodes. Totally, we have 396 wires. These are all done in the clean room, and with the expertise who are trained in this. And there are a lot of time invested and to get out of such kind of detectors. It's a very challenging job. Yeah, and this is the wireframe sitting inside the housing. Yeah, this is the wireframe that is sitting in the base plate here. And these two, yeah, there are 2 detectors just to demonstrate, and the scatterer. This is the lab picture. There are 4 detector assembly. The actual assembly is like this. And detector assembly with shield, actually, the detector assembly is shielded to reduce the penetration of off-axis X-ray photons. Actually, there are shields here. Shields are made of 3 layers, SS of 0.4 mm inside, molybdenum thickness of 0.2 mm, which is in the middle, and tantalum outside, which is 0.2 mm. The thickness of layers are chosen to absorb off-axis X-rays up to 100 kilo electron volt. Each inner layer absorbs the fluorescence X-ray photons emitted from the immediate outer layer. Coming to Polix electronics, I have just, I'll try to explain this. For polarization measurement, we need to find the azimuthal distribution of photons falling in the detector, which I also in the previous slide also explained about this. The detector has wires in the vertical direction. This is also demonstrated in one of the cut view you would have noticed. There are 12 anodes, that is 6 plus 6. The primary requirement of the electronics is to determine the detector and the wire in the detector in which the photon has finally fallen after scattering. Yeah, I have taken one such wire. This is one wire is taken here. To identify the wire on which the photon has fallen, we use the principle of something called charge division. And these anode wires are resistive nichrome wires, and these are all the wires are looped together at the ends. The photon absorbed in one cell of the detector causes the deposition of charge on corresponding anode wire, as shown in this figure. This charge will split and flow towards the two ends of the wire. This splitting of charge will occur in such a way that the end of the anode, which is farther away, um, which provides higher resistance to the flow of charge, farther away will receive less charge and vice versa. So thus, the amplitude of the charge pulses collected at the anode ends is linearly related to the distance from the point at which the photon has impinged. So dividing the pulse amplitude at one end by the sum of the pulse amplitudes at both ends, we obtain the position of the point of interaction of X-ray photons along the length of the wire. So this technique of position determination is by the concept of what is called charge division. I'll not go into the details, inside details of this. This is the basic block diagram of the payload, Polix. There are 4 detectors, which is on the top. You can see there are 4, then front-end electronics, processing electronics. As I said earlier, there are 4 detectors. These are basically proportional counter detectors with the wires looped together. For each photon falling in the detector, a charge pulse is produced. Front-end electronics converts these charges to proportional voltage pulse. Also, it provides controlled and stable high voltage bias to the detector. Processing electronics, what it does is it digitizes, actually it holds the peak and digitizes the peak values of these pulses and passes this data to the common electronics represented as C here. It also sends the total count of different types of pulses processed on every bin clock. Common electronics combines these 4 P's, time tags the data, packetizes and stores data, and transfers this data to satellite bus. Housekeeping electronics acquires and monitors important payload parameters like high voltage, thresholds like upper and lower, power supply voltages, and these things will be passed to TMTC. This data is passed to TMTC. The telemetry and telecommand that acts as a command interface between the polarimeter electronics and the satellite bus. It also passes the monitoring data and a quick look data to the satellite bus. This is another picture that is a lab picture where you can see here you can see 3 electronic units and detector and the collimator. Some more pictures. Yeah, Polix nominal flight operation. Polix payload is kept on at all times, and we are not going to power off, creating source, background, Earth occultation data, depending on satellite position or attitude. The only normal operation will be SAA operation. I'll tell you about SAA operation. This during SAA passages, the HV is reduced. HV, I mean high voltage, is reduced, but data stream with zero counts, low data rate is still generated. There are no separate modes of operations, and there are no selectable parameters for the observer. Polix has self-calibration. That's, I mean, the detector gain and position information. Gains of different detectors will be monitored using background data and will be, equalized using high voltage steps as required. Additional calibration will be required from time to time by observing some celestial X-ray sources by varying instrument parameters. So SAA, I'll just quickly comment on this. Madam, can I take a few more 10-15 minutes more? Hello?
Yes, 10 minutes.
Yeah.
Within 10 minutes, you can.
Okay, yeah.
Okay.
These solar particles are focused and given direction by Earth's magnetic field, and depending on the distribution of the magnetic field on Earth, in some regions, see a very large flux of solar power. This includes the poles too. The regions around the poles are very strongly affected by solar wind particles that is coming very close to the Earth. But there is an anomaly, it's called the South Atlantic anomaly. There is a large influx of solar wind charge particles. Here, the energy discharge particles that reach to very low altitude because of magnetic anomaly here. So if the payload enters this SA region, it experiences a large amount of charge particle bombardment, which is going to cause ionization in the detector, and it might cause a detector breakdown. So the high voltage in the detectors of Polix payload will be ramped down whenever it enters the ASA region. Yeah. So yeah, coming to beautiful, nice, another co-passenger, Expect. It's developed by SIG Group, Space Astronomy Group, ISRO, your Rao Satellite Center. This is the what I see. What you see is Expect detectors 1 and 2 on that is just sitting next to Polix detectors, and there is Expect electronics. Expect is mainly a spectroscopy instrument. Long-term observation, like weeks to months of selected X-ray sources in soft energy band between 0.8 to 10 kilo electron volt. Such a study has not been undertaken by previous instrument. Study of these bright X-ray sources in soft band with pileup-free observations, then good spectral resolution, the spectroscopy measurements along with the polarization information. Yes. There are some specifications about Expect operational to model the continuum emission from X-ray binaries. It's 0.8 to 15 kilo electron volt. Resolution required for modeling ion line profile is less than 200 eV at 6 keV. To investigate evolution of X-ray spectra is greater than 30 femtowards 6 keV. This is the specs of Expect. There are some pictures of a detector and Expect electronics that is shown here. I just want to say a few things. that X-ray spectral and timing experiment expect on XPOSAT will study the long-term temporal and spectral behavior of selected sources in 0.8 to 15 kiloelectron volt band. And these SCDs, what I showed, provide a large collecting area, 4 cm2 each sensor, total 64 cm2, along with good spectral resolution. The sweep charged devices SCDs have no spatial resolution in the detector plane. Actually, it cannot indicate where the photon interacted. However, in the absence of X-ray optics, the large volume and weight increase, field of view can be derived using passive collimators. Finally, with a fast and continuous readout of SCDs, it yields good spectral resolution even at temperatures of minus 20 degrees centigrade. So this avoids power demanding active cooling systems and permits the use of passive cooling systems like heat pipes and radiators to meet the thermal requirement. Expect has a field of view of 2 degrees by 2 degrees or 3 degrees across 3 degrees. This requires collimator of a large height, keeping open areas fraction higher. In the SA region, as I said, Polix high voltage will be ramped down, but in case of expect, it will be powered off in that duration. Yeah, there are some tests that are carried out for XPOSAT at ISRO or EMI, EMC, electromagnetic interference and compliance. And there are vibration and acoustic tests, thermovac tests, then disassemble and assemble tests, then satellite thermovac, satellite EMI, EMC, then satellite post vibration IST, and then satellite MST. Also, there are a lot of tests that were done in the lab. Let's see, once you don't have satellite in hand, so we may have to have our own ground checkout systems, wherein we will be doing similar kind of tests to qualify the payload. Those kind of things will be extensively done at a lab. There are intensive tests that will be carried out at every minute stages in any satellite. So that is done here. So I'll try to conclude. We have seen some basics of X-rays, what is XPOSAT, why it is made, working principle, and how it is made. I've tried to explain to best of my knowledge. So thank you. This is Polix team picture. I acknowledge my team. If anyone is missing, I'm sorry for that. Thank you, creative team. Thanks.
Thank
I
you,
conclude my talk here.
Okay. Any questions? You can unmute and you can ask the questions. Girish sir?
Sir, thank you very much for the wonderful introduction. Hello, can you hear me, sir?
Sir, unmute. Murthy sir?
Yes. Okay, so I just wanted to ask you, if you are asked to actually make another Polix, so what are the changes you would like to introduce? Like, I just want to know what you have learned from whatever you have done till now.
Yeah, I think in the audience, one of our Polix team senior engineer, Mr. P.V. Rishin is also there. I think Rishin, are you there? Hello.
Yes, Murthy.
Hi. So you have comments on this?
The question is like,
How do we,
suppose
like,
we do one more polix, right?
yes.
Ideally, we would like to actually go for much more better technologies which are available now, rather than going for a polarimeter based on proportional counter detectors. We may go for newer technologies like GEM or something like that. That is my opinion. Yeah. Was that the question?
Yeah, that was the question. Sir, is that
any
actually you can,
photon related method would be what we would like to go forward. Yeah.
thanks, Rishan.
Okay, Venkat.
Yeah, am I audible?
Yes,
Yes.
Venkat.
Okay, thank you, sir, for your presentation. So, I was looking to ask you forward that since this is an X-ray astronomy telescope, right?
Yeah, X-ray astronomy used for, the satellite used to study
Right.
X-ray astronomy, X-rays at space. Yes.
Right. So my question was that how are we seeing this going to be differing from current technologies that we have put right now?
What do you mean by current technology? See, as I was mentioning in the very beginning slides, there
Yes.
are various imaging, spectroscopy, and kind of things. Those kind of things have been done from decades. But when it comes to polarization measurements of X-rays, this is the second instrument, second payload. In my view, it's across the world. We have built. There are only two instruments, IXP, and then now it is from India, our Polix XPOSAT. I hope your answer is. Your question is answered.
Yeah, and I also have a second question. Can I?
Yeah, please.
Okay, so we have Polix and XPOSAT as two.
No, Polix and Expect are the two payloads.
Expect, okay.
Yes, yeah.
Then you mentioned XPOSAT, right?
Yes, see, the XPOSAT is the name of this mission, satellite mission. Okay, the payloads that are carried in this XPOSAT, one is Polix, the other one is Expect, XSPECT.
Okay, Polix, XPOSAT, and some 9 other satellites from what I know.
Yeah.
In this PSLV mission.
Yes.
So with this new mission, how does Expect and Polix both try to say add some new?
Yeah, I got your question. See, there are the major payloads. Can I answer?
Yeah, add some new experience to ISRO in a short way.
Sorry, once again.
Add some new experience to ISRO and the people who have worked in this.
Yes, see, this XPOSAT machine mainly contains only two payloads. No other payloads will be going with this. Okay, the satellite that is being launched now will be carrying various other small satellites for various purposes. It may be for projects and things like that. So they will be in the in their respective orbits, but along with XPOSAT, no other co-passengers will be going. It contains only two payloads, that is POLIX and XPECT. It's a completely different machine for the study of X-ray polarization, and this is nothing to do with any other satellites. Like as you said, there are a couple of satellites that is also going. They are all going together, but the destinations and the purposes are different.
Yes.
Yeah, I mean, see, any launch when the kind of efforts that goes from Earth to reach to low Earth orbit kind of thing, we will not be able to do. Suppose tomorrow we want to send a small satellite just like that. For that, another PSLV cannot be launched. So what we do is we combine other things also, and they are just dropped. They are just dropped on the way. Yeah.
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 Okay then. Thank you, sir.
Thank you.
Any more questions? Gagli sir. Okay, I think we can wind up here, sir. I think no more queries.
Yes.
Yes, sir. Thank you.
So
Thank
if
you
there
very
are
much.
any things, we can always, you can always contact RRI. We are there, and to best of our knowledge, we'll be able to answer your queries.
Yes. Thank you, sir. Thank you very much
Thank
for
you.
insight of XPOSAT. We are very much happy with your polite talk. Okay. Thank you very much, and we are
Thanks,
looking forward XPOSAT into the sky. Yeah.
Yes.
Thank you. Thank you
Yes.
very much. Thank you,
Hope,
one and all.
Thank you, sir. Thank you, ma'am.
Hope I could convey some information
Yes, sir.
which
Yes,
you
sir.
could understand. Yes. Yeah.
Yes, sir.
Thanks.
Thank you. Thank you, one
Thank
and all,
you.
for joining with us. We are ending
Thank you,
here.
Rishan.
Yeah. Thank you, ma'am.
Thank you, Venkat.
Thank you.